Swayam Prabha. Digital India. Educated India.
Welcome to the course on micromachining sponsored to DTH Electrochemical Micromachining Part 2. Acknowledgement. MTech thesis by Jitendra Singh, MTech thesis by Subodh Kalia and MTech thesis by Dilip Gehlot. Objectives of this lecture is to understand the experimental and theoretical aspects of ECMM process. What we have done in the last lecture on electrochemical micromachining are as follows: theory of ECM and ECMM, Faraday's laws of electrolysis, chemical analysis of ECMM processes, machine tools fabrication, machine tools configuration for ECMM process, types of the tools that can be used in ECMM, process parameters governing ECMM process, different types of operation that can be performed during ECMM process. Outline of this lecture: experimental setup, fabrication of micro holes, fabrication of micro tools, fabrication of micro mixers, fabrication of PCB, that is printed circuit board, and finite element analysis of electrochemical micromachining. This is what we are going to discuss in this particular lecture. Applications of ECMM, what we have done. Micro operations we have already seen, like micro turning, micro dipole drilling, micro electrochemical sewing, electrochemical wire cutting, tube as a wire, trepanning, etc. Industries that use this particular process are aeronautics, nuclear, space vehicles, automobiles, etc. Products that are made using this particular process include micro holes or micro cooling holes in turbine blades, curvilinear micro slots, micro hole making perpendicular to the wall, etc. I will show the figure and you will appreciate its importance. Materials that can be machined, especially difficult to machine metals and alloys, because the basic condition is that the workpiece material should be electrically conductive. Experimental setup and applications of ECMM setup process. Now here I will show you some of the setups developed at IIT Kanpur, and I have shown couple of the setups developed by other universities like Jadavpur University and abroad also. Another experimental setup, machine tool Hyper 10 used at IIT Kanpur, multi-process micro machine tool by Synergy Nano System. They are the producer of this. You can see here. Now you can see the different parts of Hyper 10. Power supply, electrolyte tank is here, tool is shown over here, workpiece, that is this one, and manual pulse generator. Operations that can be performed on this machine tool are micro ECM, micro EDM, micro drilling, micro milling. Note it carefully that here you can perform micro drilling and micro milling also. They are not electrochemical micro drilling and electrochemical micro milling, rather they are conventional drilling and milling also can be performed on this particular machine. Machine has X, Y, Z axis, feeding units, work table, ECM, power supply unit, control unit and electrolyte flow control unit. Experimental setup that was developed at IIT Kanpur by our students. You can see over here all the features that you have seen in the earlier machine tools, they are incorporated in this particular setup, like Z axis control is there, airflow control valve is there, X axis electrolyte tank, tool feeding unit, workpiece monitoring and electrolyte collecting tray, here it is there, and then you can control the Y axis movement mechanically also. Electronic circuit for stepper motor control is there. Now M. Karnik was the student at IIT Kanpur who developed this particular setup. Now you can see here some details, especially here another design of ECMM setup, different parts are shown over here that I have already told you. Now here you can see the electrolyte flow is there. Now as I have mentioned to you earlier, this is the, if this is the micro tool, then this is the external device, internal channel for electrolyte flow, and this is the tool. So electrolyte is coming along all the sides of the micro tool. Tool is there and here is the workpiece. So you have this as the inter-electrode gap, which is very important. Tool is made as cathode and workpiece is made as anode. Now the parameters, there are certain static parameters of the process and there are other dynamic parameters of this particular process. Static parameters include electrolyte, pulse frequency, tool material, workpiece material. Now you can choose their optimum values like pulse frequency and tool material, and workpiece material you cannot change because this is being prescribed by the manufacturer, and definitely electrolyte you can select according to the workpiece material. There are certain dynamic parameters like inter-electrode gap and voltage, they keep varying during the process also. Operating parameters in ECMM process, pulse frequency. Now pulse DC signal is there, this is the off time, this is the on time, and this is the group pulse DC signal. These are the groups, you have the T1, T2, T on, and this is the T off definitely. T1 is the time period of main pulse, T2 is the adjusting pulse time period, T on 1 and T on 2 are pulse on time for main pulse and adjusting pulse, where T on, T off are pulse on time and pulse off time in this particular case, and you can find out the duty cycle by T on upon T on plus T off, and duty ratio is T on divided by T off. So you can calculate these important parameters from these formulae. Now this is another schematic diagram. I need not to explain this because I have told most of these components in the earlier slides. Now fabrication of micro holes using electrochemical micromachining process. A specification of micro tool used in fabrication of micro holes. A copper wire is used as a tool. Tip diameter of the copper wire is 145 micrometer and taper angle is 11.74 degree. Now you can see this is the schematic diagram of the ECMM tool that was used over there. Now you can see the diameter, upper diameter is 214 micrometer, tip diameter is 145 micrometer, and the tapered tip length is 166 micrometer, and theta is the angle of taper. Now copper sheet having thickness 100 micrometer is used as a workpiece. Before machining, workpiece was cleaned by acetone to remove dust and impurity. If you don't clean it, you will not get the desired characteristics of the machine component. The specifications of micro tool used are like this. You can see here 281 micrometer, this is the 47 micrometer here, 98 micrometer here. So, it is because it is tapered, tape diameter this is shown over here, taper angle is 12.93 degree, and nickel coating was there on this particular tool, not here. Different copper plates having thickness 200 micrometer, 500 micrometer, 700 micrometer, 1000 micrometer and 1300 micrometer are used as workpieces. Now, chemical reactions that we have seen in the earlier lecture also, here slightly different because here we are using copper as the workpiece material, earlier we used iron as the workpiece material. So, copper will make copper ions plus 2 electrons, 2 H2O plus 2 electrons, hydrogen gas is evolved at the cathode and 2 OH minus means negative, and in solution you have copper plus OH cuprous hydroxide. Now, that settles down at the bottom. How to make micro tool with insulation? You can see here, this is the coated micro tool that has been prepared. Now, because we want the tip to be bare, so that current can flow through that. So, this much material has been removed carefully. This is not very neat and clean tool, but it should be done very neat and clean, so that you get proper hole, micro hole drilled. This is the bare bit over here. Note shear off by sharp blade not done uniformly. In this particular case, it may result in improper cutting. Tool with insulation that you have seen here, this insulation of thickness 6 micrometer is over there. This is to minimize stray current effect at the tip. Effect of stray current, as you can see, this is the uncoated tip as shown over here, and this is the coated part. So, this is shown over here. So, you can see here current is flowing from the uncoated part and it is able to machine at a much larger distance under rather from the tip rather than just machining below the tip, and this is known as stray current effect. This is insulation bare bit, stray current attack is, this is all stray current attack, and because of this you will get the dimensions which you do not want, because this you wanted this much hole diameter, but you are getting this much radius or this much hole of the drilled this much diameter of the drilled hole, and this is the inter-electrode gap in this particular case. This is the diameter as 593 micrometer and this is a diameter of 567 micrometer, but all around this you can see some material has been removed. Here also some additional material has been removed, and this is all due to the stray current attack or stray current effect that I have shown over here. And you have to have minimum bare tool height, so that you don't get too large this stray current affected zone. Insulation tool and stray current effect further. Tool with insulation perspex chips dissolve into the chloroform. How to prepare this insulation or coating on the tool? So, the person or the student dissolve the perspex chips into the chloroform. Insulation of thickness 12 micrometer was done, or a layer of 12 micrometer thick was coated on the micro tool. It minimizes stray current attacks at the tip that we have seen already in the earlier slide. The distribution of electric flux lines during ECMM process is such that a part of the workpiece which is far away from the tool also undergoes dissolution. That is, this is the far away part of the tool workpiece, where we do not want the material to be removed. This also undergoes dissolution due to electric current lines acting over this side. These are the electric current lines, they are acting over here. Material removal from such areas is called stray current zone machining, which is undesirable not just because of poor dimensional accuracy, but also because etched and pitted surfaces are obtained in this zone. As we have seen in the earlier slide, there pitted surfaces were there in this particular zone because of the stray current attack. Empirical modeling for predicting micro hole diameter. Empirical model but developed using statistical technique based on the experimental result. This is the experimental result. Now, there are various kinds of the models. You can have a theoretical model, you can have a empirical model. So, this is the empirical model which has been developed using a statistical technique based on the experimental results obtained by the student. Now, you can see here this is the hole diameter where V is the voltage, C is the concentration, D is the diameter of the tool, and F is another constant I will show you. F is the feed rate, right. So, one can use this particular empirical model, but please note it that empirical model is valid only for the given tool material, given workpiece material and given machining condition. If you change any of them, then these empirical models cannot be used for predicting the hole diameter accurately. Now, here the coefficient of correlation for the given relationship is 0.914. You can clearly see the individual parameters effect V, C, D, F are the individual parameters. Their interaction effects V C, V D, V F etc. that you can see V C, V D, V F etc. and higher ordered effect where we have the V square, C square, V square, D square, F square. So, with these empirical models we can easily see the individual parameters effect, their interaction and their higher order effects, which is difficult in theoretical models. Caution: this model is applicable only for the given tool and workpiece materials and the experimental conditions under which the experiment were performed. You can easily develop such models using the above procedure, and softwares are available which can be used for this particular purpose. Prediction of micro hole diameter using the above developed model. You can see here this is the hole diameter and this is the voltage. As the voltage is increasing, hole diameter is increasing. Now, you can see here this is for one feed rate, this is for another feed rate. This is 0.1 and this is 0.2. So, if voltage is increasing, material removal rate will increase. Hence, you can see with increase in voltage, diameter is increasing. If feed rate is slower, means the tool is staying at a particular point for a longer period, then the material removal will be more, and that is why you have the higher hole diameter as dotted shown over here. Same way here hole diameter with concentration, same thing is there, that as you increase the concentration up to a certain point, the diameter is increasing. This is at 7 volt, this is at 8 volt. But beyond a certain concentration, what happens, the electrolyte conductivity starts decreasing beyond this particular concentration, and if the electrical conductivity of the electrolyte decreases, then definitely current flowing will decrease, and current flowing is decreased, current density is decreased, so material removal rate will decrease. So, you can see the hole diameter is also decreasing if electrolyte concentration is increased beyond a certain level. Then feed rate, as I have explained earlier, that if lower the feed rate, higher will be the diameter of the if lower the feed rate, higher will be the diameter of the hole being drilled. Or you can see as the feed rate is increasing, hole diameter is decreasing. In both the cases, this is with 15 gram per liter concentration, this is with 25 gram per liter concentration. As we have seen over here, beyond 25 it will start decreasing the conductivity of the electrolyte. So, this hole diameter also will start decreasing. Now, here it is the duty cycle. As duty cycle is increasing, hole diameter is increasing. Now, for different voltages, it is lower for lower voltage, higher for higher voltage, as we have seen over here also. through microchannel cutting. Please note, tapered tool results in tapered microchannel. See front and back side of channels, bits and its variation due to non-uniform cutting, that is due to the improper coating. I have shown it to you in the earlier slides. So you can see over here front side of the machined microchannel or the top side of the microchannel, and you can see the non-uniformity in the channel being cut. And this is the back side of the microchannel, and you can see it is smaller than this, and this is like this. So it is non-uniform and it is smaller than the front side, because as the inter-electrode gap increases, the current density decreases, so material removal rate will also decrease. So that's why you have the smaller dimension of the channel at the bottom side. This is the tool. This I have already explained. So you can see here this tapered channel is being obtained, and it is larger diameter at the top, smaller diameter at the bottom. So this is the larger diameter at the top, smaller diameter at the bottom, and non-uniform due to the improper coating in that particular case. So taper angle 77.92 degree, this is the taper angle, and tool taper angle 12.93 degree. So you can see the difference. This is the taper angle as shown over here. These are the different machining parameters. Fabrication of micro tools is another challenging task. Some idea I had given to you in the earlier lecture also about the fabrication of microstructures using electrochemical micromachining by Subodh Kalia. Micro tools fabrication by electrochemical dissolution. Earlier lecture I had told you about the various techniques used for fabrication of micro tool using EDM and wire EDM processes. Here he has used, Mr. Kalia has used it, electrochemical micromachining process also, apart from electric discharge micromachining and ultrasonic micromachining, which can be used for this purpose. Micro tools fabrication is not that easy. Now here experimental setup is given over here. This is the negative copper is the tool, and this is the anode, and here anode is dissolving, so its diameter is continuously changing. You can see over here, this is connected to the positive terminal, this is for the negative terminal. 1300 micrometer copper wire was used as the cathode, 1000 micrometer iron wire was used as the anode, and 0.1 m H2SO4 solution was used as the electrolyte, that is the acidic electrolyte. Now chemical reactions that were taking place, we have already seen these chemical reaction where ferrous hydroxide is generated or produced, or under certain circumstances you can have the ferric hydroxide also, and both are undissolvable in the electrolyte. For uniform dissolution and uniform diameter, anode can be rotated along its axis. If anode is rotating, then you will get better accuracy of the micro tool that you are going to prepare. Fabrication of micro tools continued. Using the above experimental setup, following micro tools were fabricated at IIT Kanpur. You can see here, this is a 1000 micrometer diameter wire, starting wire, and 604 micrometer wire that its diameter was reduced, and then its diameter came down to 100 micrometer, same from 1000 to 100 micrometer, and finally the tool that was achieved using this process was 80 micrometer diameter tool was used, and this tool was later on used for electrochemical micromachining processes. Uniformity in wire diameter. Rotate the anode for better results. I have already mentioned it in the earlier slide, because you can see here it is not very uniform wire, and the student did not rotate the tool did not rotate the workpiece, hence you get the non-uniform diameter of the machined wire or the tool, obtained tool. Variation in diameter with time. Now you can see here how the diameter of the wire or the obtained tool was reducing with time. So this diameter was measured at different times after certain number of minutes, say 5 minutes, 10 minutes, 15 minutes, and you can see from 1000 micrometer it came down to 80 micrometer over here after about 65 minutes. This time will depend upon what machining conditions you choose, that is the current, electrolyte conductivity, inter-electrode gap, pulse frequency, etc. So as resolution time increases, the wire tool diameter decreases, as we can see over here, almost linearly, except at a couple of points where it has become non-linear. You can see here and here also it has become non-linear. Depends on the accuracy of measurement and control of the input parameters. Variation of MRR with time. Efficiency you can calculate using this particular formula. Volumetric material removal rate is zeta I E over divided by F into rho A, and R is the resistance, rho L over A wire resistance, and V is voltage, IR current and resistance. So L is the inter-electrode gap, rho is the 1 over K, A is the cross sectional area of wire, V average is the average volume removed. You can see here average MRR removed. This is time and this is average MRR cubic millimeter per minute. It starts increasing and then it more or less stabilizes. You can calculate V average, or this has been calculated from pi R2 square minus R1 square multiplied by length L, or MRR average, V average, that is the volume average removed divided by time. So you can calculate either total volume of the material removed from the wire or material removal rate from the wire. As machining continues, A decreases, that is the cross sectional area that is given over here. L remains constant for wire, that is the length or inter-electrode gap, but inter-electrode gap increases. This L is the length and this is the inter-electrode gap. Overall effect is that I increases, hence MRR increases. Beyond a certain value of time, the rate of decrease of MRR decreases because of the changes in the above three parameters. You can see the decrease is there. Micro mixer fabrication, this was done by Subodh Kalia. Now this is the micro mixer that was needed or developed in the manufacturing science lab of IIT Kanpur. You can see here one fluid is coming from this side, another fluid is coming from this side. Both fluids, they are getting mixed up over here. This is the mixing chamber and mixed fluid is coming over here as the output. So this is the designed mixer. These are the different dimensions of the mixer. Now you can see this is 250 micron, this is 1000 micron and so on. Different dimensions are given over here. These are the length in millimeter and this is the width. Now here this was fabricated, no addition of mask on workpiece. Here no mask was adhered over the workpiece and machining was done, and you can see here the non-uniformity in the dimensions, and this is the additional stray current effect material is there. So it is not giving very good picture over here and not high accuracy of the machine features over here. Overcut underneath. Now these are the different machining conditions that were used, and sodium nitrate was used as the electrolyte. mask fabrication. Now, how to prepare the mask for such a small mixer making? So, this was done with the help of the laser cutting. Now, you can see here, these are the different dimensions that were obtained on the mask with the help of the laser cutting. Now, this is the part, as you can see here, bare part where there is no mask, because from here the material is to be removed. So, these are the parts or bare parts where from the material is to be removed from the workpiece, and whole of this is made up of electrically non-conducting material. 50 micrometer thin transparent sheet was used for this purpose for making this mask, cut using laser cutting machine, and 15% raster speed and 16% laser power was used. You can see here, this is the tool, this is the workpiece, and this is the mask where mask is to be adhered on the workpiece, and this becomes the inter, because this top face of the workpiece and bottom face of the tool, that gives you the inter electrode gap. Workpiece is positive and tool is negative. Fabrication of micromixer. Addition of mask on workpiece was done using water insoluble glue. This is very important, it should be water insoluble glue, because it is to be immersed inside the electrolyte. See cleanliness of machine mixture compared to the earlier case of mask addition with water soluble glue. Now, this is the finally made mixer, and you can see the difference in this mixer and the earlier mixer which I have shown you 2 slides back. So, this is comparatively more neat and clean, and you can see the dimensions. All this is 285 micrometer, 381 micrometer, 285 micrometer. So, what is happening here I will show you. One fluid is coming from this side, another is coming from this side, and both of them are getting mixed up and they are going out from here. Now, you can see here, this is the region 1, region 2, region 3, or this is the region 4. Mixing is taking place in the region 4. So, these are the different dimensions that have been obtained in terms of micrometer: region 1, region 2, region 3, region 4. 3 steps: mask preparation and addition, electrochemical micromachining and removal of mask, depth measurement at different locations of each region, testing of micromixer. Whatever micromixer was prepared in the earlier slide, that was tested, and let us see how well it works. Mixing at volume flow rate of 20 milliliter per hour. It is a micromixer, so definitely volume of the fluid will be low. Now, you can see here, this is the fluid, black ink is coming from here, and this is the fluid to water is coming from here, and both of them are getting mixed up. Here you can see slightly difference in the color, and here you can see single color. Mixed fluid is going, interchange of fluid stream. This is the mixing chamber. Either anyway, we need not to worry about this Reynolds number, etc. All these things. Mixing fluid 1 and mixing fluid 2 have different colors, while the mixed fluid has a single color. That I have told you, this, and this. These are the 1, 2, and now how to working, design and fabrication of a nozzle. This is the nozzle, you can see input fluid is there, this is the output fluid. These are the different dimensions and angle of the nozzle that was prepared. Now, you can see here prepared mask. This is the mask for that purpose, for making the nozzle, because this is the area where there is no mask, and this is the mask over there. So, material will be removed from the area where there is no mask. So, remove the laser cut part for EC dissolution of anode. This part, as this arrow should be up to this particular point. This point, this arrow should be here. Fabrication and specification of micro nozzle in different zones. This is the mixture. This is the nozzle that was fabricated, and you can see this is the 1200 micrometer. This is the dimension shown over here. The second part 1970 micrometer. However, this is slightly larger than 1 millimeter, so I have little bit hesitation in calling it as a micro mixer, but this was prepared accordingly. But here, if you see, sorry, this is micro nozzle, not mixer. You can see here, this was done over here. This is the 264 micrometer, so you can really call it as a micro nozzle, because final dimension going through this nozzle is the 264 micrometer. 293 micrometer, so you can see the non-uniformity in the size of the nozzle, and this is the 1910 on the other side. So you can see different dimensions of the micro nozzle that was prepared in the lab. Now machining conditions were used as 5 volt, because we have already seen in electrochemical micromachining it is normally less than 10 volts. T on time 1000 microsecond, T off time 400 microsecond. Sodium nitrate as the electrolyte with concentration 15 gram per liter of water, and inter-electrode gap as 1000 micrometer. Finishing of micro nozzle. This is very important, because as we have seen in the earlier slide that the surfaces of this micro nozzle are very rough, as you can see here also, and in the whole part these surfaces are very rough, so they cannot be used as such, so they have to be finished. So finishing operation is required to smoothen the rough edges and bottom surface, hence magnetorheological finishing MRF is done on the fabricated nozzle. Mask arrangement for finishing. This is the mask, this is the area exposed for finishing purposes, this and this area, and this is not. So this is the magnet which is having the carrier, magnet carrier is there, and here workpiece is there, and other CNC head etc. are there. This is connected to the CNC machine. You can see here before it is so rough, and after finishing you can see the difference between the two surfaces. This part before finishing, this is after finishing, and this is before finishing, after finishing. So MRF can be used for finishing of micro surfaces, micro features or micro products. You can see the whole nozzle, this is before finishing, this is the after finishing, and these are the sections. So it clearly indicates the substantial difference in the finished surface. Qualitative difference before and after. Fabrication of complex circuit, very important, and this process can be used for fabricating the PCB, and this was done by Mr. Jitendra Singh. This is the circuit which was designed. And this is 0.05 millimeter thin transparent sheet cut using laser cutting machine. This is for the masking purposes. So whatever dimensions are here, those dimensions they are cut with the help of laser cutting machine. Now one thing you should see clearly the difference, because if here many places this here this is not completely cut, otherwise it will not be possible, it will be difficult to keep them adhered or keep them joined all the parts, and it will be difficult to adhere it on the PCB. So this effect we will see in the machine component. How it was done? Tool was there, mask was there, workpiece was there, and workpiece was positive, tool was negative. Now this is the one addition of mask on workpiece using water insoluble glue. So, this is the mask that has been adhered on the workpiece. Now, you can see here these are the open areas where from material will be removed, but in these open areas here there is no open area. So, that will really, here there is no open area. So, in fact this is not the one that you will like to have as the actual or real life PCB, printed circuit board, but in fact just this was the first attempt made by anyone in creating PCB using this micromachining, electrochemical micromachining process. So, this was not done, but later on one can do remove these parts and glue the mask on the sheet, so that you get proper printed circuit board. Effects of input parameters on complex circuits. Measurement of circuit dimensions, depth and width of channel were measured, because these are the channels, micro channels, and their depth and width were measured, and these are the photographic views of this. And voltage used was 7 volt, capacitance 10,000 picofarads, sodium chloride concentration 25 gram per liter as the electrolyte, and interelectrode gap 1000 micrometer. Please note it carefully that in earlier cases also they have used quite large interelectrode gap, that is 1000 micrometer, which is really too big, but keeping in view the facilities and other constraints, this was very high. Otherwise, in micro machining, this interelectrode gap should be few tenths of micrometer only. You can see here voltage capacitance, and this is the one that has been fabricated. So, these are the areas where from no material has been removed. Here also no material has been removed. Now, the width measurement of different sections, you can see here these are the actual photographic views. So, you can clearly see the non-uniformity in the material removal. So, to use it on shop floor or in industries, one has to do lot of work in this PCB making by electrochemical micromachining before really it is put to the shop floor. Now, you can see from here, because the mask was there, so no material has been removed from here, but rest of the area material has been removed. So, you can see again non-uniformity here as well as here also. So, this clearly indicates that their control was not very good, mask was not cut, hence no machining took place. At other places also it shows improper laser cutting of the mask, because you can see here as well as here, since mask was not cut properly, so that has been reflected here after electrochemical micromachining. Now, circuit fabricated by electrochemical micromachining, you can see here circuits fabricated by micromilling. Now, this is the conventional micromilling, but this was directly fabricated on the sheet, and it takes lot of time in fabricating this compared to this whenever there is a problem of mass production. In mass production, electrochemical micromachining may prove to be better and faster than conventional micromilling process. Micromilled circuit seems to be more clean than electrochemically micromachined one. Improper cutting of the mask by leaving unmachined areas on the mask, as you can see here, as well as here. Electrochemical micromachining is a multi-step process, while micromilling is a single step process like this here. Anode shape prediction in ECMM. This work was done by Mr. Dilip Gehlot. Now, let us discuss in very brief anode shape prediction ECMM. I will discuss it in detail later on in the another lecture, where I will deal with anode shape prediction and tool design. Anode shape prediction is also known as analysis problem of ECM and ECMM, and cathode shape prediction also known as design problems. Now there are various methods, details we will discuss in some other lecture. Like for anode shape prediction, that means workpiece shape that you are going to get after electrochemical machining and electrochemical micromachining. So various techniques have been developed. One of them is cos theta method, another empirical approach, complex variable approach, finite difference method, finite element method, boundary element method. These are the various methods that have been used for anode shape prediction, and the same with some modifications have been used for cathode design or cathode shape prediction that will give you the desired workpiece shape. They are cos theta method, complex variable approach, finite difference method, finite element method, boundary element method, and lastly lately developed was error function method that was developed at IIT Kanpur by one of the master's student. Variation of current density. Current density is here, distance is here, as you can see here that continuously the current density is varying, and as the time increases the current density is decreasing, and this is the time given in seconds. So you can see here the variation of current density with time at voltage 8 volt, inter-electrode gap as 200 micrometer, and concentration of electrolyte as 30 gram per liter. Now variation of current density with distance and time both are whatever I have shown there. This is the one and this is the another one for time 20 seconds, and this is for 40 seconds, and this is for 2 seconds. So you can clearly see that with distance as well as with time the current density is continuously varying. It can be easily seen that as the machining time increases, undercut increases, but after a certain value the rate of undercut decreases because of decreasing the current density in the lateral direction. So you can see here different timings. Now prediction of anode shape using finite element method on MATLAB platform. I am not going to discuss details of this, how to develop the model and other things, but I am just giving you some idea so that you can have some idea how well it can be tackled. So you can see here this is the inter-electrode gap, and this is the finite element mesh, this is the tool is there, and this is the workpiece over here, and here it is the mask. This is the mask, this is the mask. So this is the undercut. This is the undercut on the workpiece, which is undesirable, but it is going to happen it. And these are the mesh generation. Triangular meshes were used by Dilip Galot. Mesh size was 50 micrometers. So you can imagine how small the mesh size was there, and how many numbers of the meshes should be there in this inter-electrode gap. MATLAB platform was used. Machining time was 200 seconds. Input parameters were voltage, inter-electrode gap, tool and workpiece material, electrolyte concentration, and maximum machining thickness was 1 millimeter, and number of elements used were 8000. So you can think of how much computational time will be required for handling such a small problem. Comparison of predicted and or simulated and experimental anode profiles. So you can clearly see here the deviation between the experimental undercut and this is the actual or simulated undercut. Here is the simulated undercut and actual undercut. So there is a big difference between the two. Also along the whole depth there is a deviation in the experimental shape as well as the simulated shape. Somewhere it is larger, somewhere it is smaller, depends upon the variation of the machining conditions in the inter-electrode gap. That is why you can see here, and because there is not efficient flushing of the sludge that is being formed and the temperature that is changing, that is why you can see here some we are larger than the simulated one, and somewhere is smaller than the simulated one you are obtaining. Experimental profile is compared with the simulated profile. During evaluation of simulated profile, it is assumed that all the current flow is used for the anodic dissolution and flow of electrolyte is uniform, and both of them really do not hold true during experimental conditions, and that is why you can see the difference between the simulated and the experimental profile. Both the assumptions are far away from the reality, that is why this difference is there. Experimental profiles, you can see here experimental profile for the hole, blind hole that has been made, that is 970 micron, this is 2.48 millimeter length. Another one, another picture, same one. You can see here this is 2.18, this depth is there, 900 micrometer, and this is a maximum cut. So you can see you can achieve the micro cavities or micro dimples using electrochemical micromachining very easily. Some more applications of electrochemical micromachining. This is very important, as I told you in the first lecture also, that if you want to, turbine blade is there, in the turbine blade if you want to drill the micro holes, this is the process which was used in the beginning and it is being used successfully. So you can see here this is the nozzle and these are the micro holes that are being drilled in the turbine blade. Deep cooling micro hole drilling, this is the one that you can see, this is the insulated tool, deep hole turbine blade. Operating parameters that I have shown. Now patterning of features in single step. In single step you can create such kind of feature. This is the experimental part machine photograph, and these are the machining conditions. Concentration 20 gram per liter, sodium nitrate, interelectrode gap 1 millimeter, and duty cycle 0.476, and you can see here all the dimensions of the machined machined pictures or features. Photographs of stepped micro tools, they can be produced. As you can see here, these are the largest diameter, smaller diameter, and then smaller diameter, and there is a tip which is still smaller than this. So you can see here they are shown over here. Larger this has been enlarged or magnified view, and you can see here clearly 10 parts, 11 parts are there. Final diameter 0.337 millimeter, that is 337 micrometer. Tip radius is 45 micrometer. So tip radius over here they were able to achieve 45 micrometer. You can see here tip radius is 104 micrometer and final diameter 450 micrometer of the micro tool, if you want to call it as a tool. So what we have done in this particular lecture, let us see. Experimental setup of different types made by different researchers, fabrication of micro holes, fabrication of micro tools, fabrication of micro mixers, fabrication of printed circuit board, very important application, and finite element analysis of electrochemical micromachining. I have not done it in detail, I will deal it in another lecture. So advice to the users of electrochemical micromachining process: always design the tools, mass and optimize the machining parameters for accurate electrochemical micromachining. This is very important. Thank you very much.